All right, for number 18, A is 190 feet per second. B is 2 seconds. C would be after 8 seconds, and its velocity was 0 feet per second at that point. For part D, after about 11 seconds, it was falling at about 90 feet per second at that point. E, it's at about 3 seconds. And F is just before the engine stopped. From t equals 2 to t equals 11 while the rocket was in free fall is the answer to the second question for part F. Why not just make a part G?
Yeah.
If you're going to ask 2 questions in one part. And then you did 20 also, correct?
Yes.
So for part A, the velocity equation is v of t is equal to negative 3t squared plus 14t minus 14. For part B, A of t is equal to negative 6t plus 14. C, there are 2 times. T is approximately 1.451 and t is approximately 3.215. Part D, the particle starts at the point s equals 8 and moves to the left until it stops at s is equal to negative 0.631 at time 1.451. Then it moves to the right until s is equal to 2.113 at time t equals 3.215, where it stops again and then continues to the left from there on. Did you do 22? Yes? 24. Ooh. At t equals 1, 0 meters per second. And again at t is equal to 2, 1 meter per second. Did you do 26?
Nope, 34. Yes. We did? I did 26. Oh, I did do 26.
On the graph paper.
Yes, you did.
All right. So pull up Graphmatica. Yes, I want to open it. Resin frickin' foul. All right. So, I don't want to rescale the whole thing. So your velocity graph, I'll just draw the shape of it, is going to look sort of like that, where this high point is at 5. And then your acceleration graph is going to look sort of like that, where this is like at, I don't know, 27 or so.
Mr. Davis, it's not on the screen. My graph does look like that.
It's on my screen. That sounds more like a you problem than
I'm sorry, I'll just get up and
everyone come up and stand around my computer. Sorry about that. All right. So the acceleration graph looks something like this, where this is 5 and that's 27-ish, 26, somewhere in there.
Yeah. Oh.
And the other graph looked like that. Más menos. Part B, ds dt, is 30t minus 3t squared. And d squared s dt squared is 30 minus 6t. Oh, so I guess that's 30, not 27. And then it says, the graphs are very similar. I'm assuming they're talking about your hand-drawn graph too.
the calculator.
All right. What's next, even-wise?
34? Yes.
34. Part A, it's 16 pi cubic feet of water per foot of radius. Okay. And part B, it's by about 11.092 cubic feet. Was that the end of the evens?
No. 42 and 44.
42 and 44. Wow.
We have multiple choice.
42 is C. 44 is E.
Can you do 34?
Probably.
Oh, yeah.
34. Inflating a balloon. All right, the volume of the volume, V equals 4/3 pi r cubed of a spherical balloon, changes with the radius. Spherical balloon. Okay. I sometimes laugh at things like that. It's like, really? Haven't seen a lot of spherical balloons, but okay. At what rate does the volume change with respect to the radius when r is equal to 2 feet? All right. So if the volume is 4/3 pi r cubed, then the change in the volume with respect to the radius, dv dr, is 4 pi r squared. Correct?
Yes, I just did 4 pi r, not 4 pi r squared.
Oh, oops.
Yeah.
So when the volume increases, how much does the volume increase by? Oh, by approximately how much? Okay. So I was thinking about a way to do this other than actually substituting it in. That you guys would understand at this point. Because I'm like, oh, I could do that, but you guys don't know about that yet. Oh, okay. So the change in the volume can be approximated then by 4 times pi times 2 squared times 0.2. Because if the units on this was cubic, does it give us any of the, oh, it's feet. So that's cubic foot per foot of radius, right? So if I want to know the change, here this is just in square units. I'd have to multiply it by the change in the radius also. So it's changing at this rate per foot change in the radius. And what was the change in the radius? It was 0.2. Okay. That makes sense?
Yes.
Okay. Any other questions? Nope. Okie dokie. I like doing that. It's not quite as satisfying as a lottery scratch-off ticket, but it kind of is. All right, I'll quit playing around. Let me give you your notes. So, derivatives of trig functions. Now, y'all haven't done that in physics, have you?
We have not.
Uh-huh. Okay, so let's try this. Grab your calculators. And let's graph. Oh, and be sure that your calculator is in radian mode, not in degree mode. That's going to be the one thing that's going to be difficult for all of you who are taking AP Physics, is that AP Physics, everything is in degrees. In calculus, almost nothing is in degrees. I say almost nothing. Every once in a while, there'll be a problem that it's a word problem that talks about degrees, but it's almost always radians. And there's actually a really good reason for it. It has to do with the derivative. It doesn't really work very well if it's in degrees. You have to multiply by a factor to get everything to work out. So let's graph sine of x, and let's make it bold. Tell it to read Joshua 1:9. And now we're going to do the derivative of that, Math 8. And let me show you something just real quick here. You can take the derivative of sine of x, but especially if this is a nasty function and you don't want to retype it, you can do alpha trace, and that pulls up the y variables. And you can just say, I'll take the derivative of whatever's in y1. Okay, because it's trig, I'm going to do a zoom trig. This morning's class was like, there's a zoom trig? It's like, yeah. So there's our graph of sine. And here is the derivative. Takes a lot longer because it's calculating. What does that second graph look like?
Cosine.
Cosine. Okay. So let's test that by adding a third function, that is cosine of x. And so that I can see it, I'm going to come over here and make it the little follow ball. And look how nicely it follows the graph of the derivative. That's fairly convincing. If you want to be more convinced, you can look at the table and look at y2 and y3. And to, 4 decimal places, that's pretty convincing. All right. Now, I do want to show you why the derivative of sine of x is equal to cosine of x analytically. But let's go back to the graph for just a second real quick. And actually, let me use this and let me graph y equals sine of x. You don't need to copy this or anything, just watch for a second. And let's zoom in a little bit on that. Okay. So, if I look right here, what is the derivative at this point?
0.
0. Be nice if I was on the right spot. 0. And right here,
Also 0.
also 0. And what does the derivative appear to be here?
1.
1. Oh, okay. And if I connect those with a nice smooth curve, what does the derivative look like here?
Also 1.
Yeah, it looks like it's pretty close to -1. So that looks a lot like cosine, doesn't it?
Sure does.
Okay. So again, the calculator did it for me, but I can also do it by hand and be relatively well convinced that the derivative of sine is cosine. Now, In order to be able to show that that's true analytically, you have to know these two limits. This one we do know. Sine of h over h as h goes to 0 goes to 1. We've done that a bunch. This is one we have not done. The limit is h goes to 0 of cosine of h minus 1 over h goes to 0. You're like, that's interesting. This is a 0 over 0 that goes to 1, and this is a 0 over 0 that goes to 0. Remember, 0 over 0 is indeterminate. It could go to anything. It might go to e for all I know. Okay? Let's real quick verify this one before we go on, that cosine of h minus 1, that's not what I want. That's what I want. Let's clear all this stuff out. So I want the graph of cosine of x minus 1 over x. So cosine of x minus 1, which is not the same thing as cosine of x minus 1, over x. Graph that. If I start tracing it, notice at 0, this function doesn't exist. There's a hole there. You just can't see it because the axes are filling the hole. But is it pretty obvious that that's going through the y-axis at y is 0? Okay? So we're at least graphically convinced of this. All right, so here's how this thing works. By definition, the derivative with respect to x of sine of x is the limit as h goes to 0 of sine of x plus h minus sine of x over h. That's the basic derivative definition that we've been using over and over again. So what we can do then is use the sum identity that says sine of x plus h would be sine of x cosine h plus cosine x sine of h. Does that sound familiar to you at least? You may have forgotten it. I don't remember the sum and difference identities because I just don't use them very much in calculus. Minus sine of x all over h. All right, well, then what are we going to do? Well, this is where it gets a little tricky. What we're going to do is take this first term and this last term and factor a sine out of both of those. So that'd be sine of x times cosine of h minus 1 all over h plus, now I still have this term, cosine of x times sine of h over h. All that makes sense to you mathematically, that's algebraically legal?
Yes.
Okay. Yeah, the math police aren't going to come get us. So here I just wrote this sine of x that was in the numerator just as a multiplier. Plus, same thing here, the cosine of x times this. This we showed goes to 0. So that'll be sine of x times 0 plus cosine of x times, well, sine of h over h as h goes to 0 goes to 1. And we end up with cosine. Okay, I always want to know who was the first one to figure that out, because it's pretty impressive. I mean, it really is. You used the definition, you used a trig identity, you used a tricky way of factoring, and used an obscure limit that I didn't even know before this. You're like, someone was on his game when they figured that out.
They're just playing around with it.
You're like, oh, wait.
Like, wow,
Look-
look at that.
Look what I found. That's called proof by accident. You're playing with something, you're like, hey, what do we have here? I used to have a t-shirt that has different ways of doing all kinds of proofs. There's proof by accident, there's proof by necessity, where it's like, well, if this isn't true, then all of mathematics falls apart. So yeah, it's got to be true. There's proof by intimidation. Don't be stupid. Of course it's true. There's several of them.
I like that one.
Proof by intimidation.
Yes.
Proof by postponement. The proof of this is long and arduous, so it's in Appendix 3. All right. In a similar way, we could show, and I'm not going to take the time to do it, that the derivative of cosine of x is equal to negative sine x. And you're like, wait a minute, why is this one negative? Well, real quick, if we graph cosine of x instead of sine of x, and just kind of sketch some points, derivative here is 0, derivative here is 0, derivative here is 0. Derivative at this point looks like it's about negative 1. Derivative at this point looks like it's about positive 1. And you can see now if I stitch those together, that's not the graph of sine, is it?
No.
It's the sine graph flipped over the y-axis. So it's the opposite of sine. Okay? All right. Now we can actually make good use of the product rule. Before now we've had products, but most of the time it was like, why would you use the product rule on that? Why not just multiply them together and then take the derivatives of the individual pieces? Now we have something where we can't do it any other way but the product rule. So here, the derivative, f prime of x, I'm going to keep the first factor, x squared, times the derivative of the second factor, the derivative of sine being cosine of x, plus, this time I'll switch it, I'll keep the second factor, sine of x, times the derivative of x squared, which is 2x. There's not much we can do in the way of simplification for this, although I will say it's standard to write polynomials before you write trig functions. Hang on a second. And the only reason for that, there actually is a good reason. Sometimes it's like that's just the way people have done it, is that this could theoretically be confusing to someone and they would think that it's sine of 2x squared. Okay? All right. We can also do things like this, where u is equal to cosine of t over 1 minus sine t. Well, we can use the quotient rule on that. So the derivative of u with respect to t is going to be the denominator, 1 minus sine of t, times the derivative of the numerator, the derivative of cosine is negative sine of t, minus the numerator, cosine of t, times the derivative of the denominator. What's the derivative of the denominator here?
Negative cosine?
Pardon?
Negative cosine?
Yep, negative cosine of t. And just generally speaking, when you're doing the quotient rule, I think it's really a good idea to put each part in a set of parentheses. It's really easy to make mistakes otherwise. It's not an absolute requirement. All over 1 minus sine of t quantity squared. So distributing here, I'm going to have negative sine t plus sine squared t plus cosine squared t over 1 minus sine of t quantity squared. This one I can use a trig identity that I hope that you still remember.
Sine squared plus cosine squared is 1?
Yes, sine squared plus cosine squared is 1. So the numerator now is 1 minus sine of t, and the denominator is 1 minus sine of t squared. This is equal to 1 over 1 minus sine of t. We will simplify things as much as we can. Just know, and this won't be, it won't be a free response question on the AP exam. If they had one like this, it would be a multiple choice, and they would simplify it, which is why we practice simplifying them. All right, page 2. Wow, there's 4 pages. I need to go faster. All right, so a weight is hanging from a spring and is stretched from its at rest position at y equals 0, 6 units, down to y equals -6. Then released at time t is equal to 0, so that its position is y equals -6 cosine t on the interval from 0 to 15 seconds. What are the velocity and acceleration at time t? Okay, so that's the position function. So the velocity is going to be -6 cosine t, -6 times the derivative of cosine t, which is negative sine t. So that's 6 sine of t. And the acceleration is going to be the derivative of the velocity. So that'll just be 6 cosine of t. So if we're trying to describe the motion, and I think I've already told you, I dislike the way your book asks the questions about describe the motion. If I was going to ask you a question like that on a quiz or a test, I would say, during what time interval is the particle moving up? Or when is it, like I think they asked about speeding up and slowing down, right? Speeding up, velocity and acceleration working together, either forward or reverse. Slowing down, one's positive and the other one's negative, okay? Those are more the kind I would ask. But since they asked on this, you're like, okay, fine, I'll describe the motion. So this starts, the weight, I shouldn't say particle, I'm so used to particle problems, starts at y equals -6. And is the velocity positive or negative once we get off of t equals 0? Once we move just a little bit, like t equals 0.1, is that going to be positive or negative? Positive, right? Because sine just past the origin, just to the right of the origin, is positive. So, and moves up. Until, well, when is it going to start moving back down? When the velocity is 0. Until 6 sine of t is equal to 0, which the first time that that happens is t is equal to pi. At which time the weight is at, we should give the position. Well, let's see, at t equals pi, at pi, cosine is -1, so this would be at y is equal to 6. And you could go on from there, right? Again, I don't like these partly because they're so long to write. It's like, yeah. Okay.
Cosine of pi is 0.
Cosine at pi is -1.
Oh, yeah, pi.
You were thinking pi over 2?
Yeah.
Gotcha. All right, let's move on. So derivatives of other trig functions. If you know the derivatives of sine and cosine, you can generate all of the other ones using the quotient rule. So, for example, the derivative with respect to x of tangent of x is the derivative with respect to x of sine of x over cosine of x. So using the quotient rule then, that would be cosine of x times the derivative of sine x, which is cosine of x, minus sine of x times the derivative of cosine of x, which is negative sine x, all over cosine of x squared. Well, that's going to be cosine squared x plus sine squared x. Hey, look at that. Over cosine squared x. So that's 1 over cosine squared x. And what is 1 over cosine? No, secant. So the derivative of tangent is secant squared. So if you know the quotient rule, the derivative of sine and cosine, and a little bit of your pre-cal. Yeah, I don't know the little bit of pre-cal.
Well, I know pre-cal, but identities are rough sometimes remembering them.
Well, sine squared plus cosine squared shouldn't be a big deal. And 1 over cosine is secant shouldn't be a big deal either. Yeah, I'm not going to ask you for some of the more exotic ones. They just don't come up very often. Okay? So the derivative of tangent is secant squared. Likewise, we could do all of these.
We should.
The derivative of cotangent is negative cosecant squared. The derivative of secant is secant x times tangent x, and the derivative of cosecant x is negative cosecant x cotangent x. Now, question always comes up, well, how do you remember all that? It's a lot to remember. All right, well, I remember two things. One is that the derivative of all the cofunctions are negative. The second thing I remember is the ones with secant and tangents, it's always two secants and a tangent. If I've got tangent, I need two secants over here. If I've got a secant, I need another secant and a tangent. It's always two secants and a tangent. That helped me remember it when I first learned this sometime in the late 70s, early 80s. All right. So let's find the equations for the lines that are tangent and normal to f of x is equal to tangent of x over x at x equals 2. You may use your calculator. Oh, well, that's pretty cool. Support graphically. Okay, so I want to know, well, what is f prime at 2? And while I could use the quotient rule and do that, I'm going to have to use a calculator anyway. So one of the 4 things you're supposed to be able to do on a calculator is find the numeric derivative at any given point. So I want to find the derivative with respect to x of, what was it, tangent of x over x?
Yes.
Thank you. Tangent of x over x at x equals 2. So 3.433. Oops. Didn't mean to do that. There we go. So now I can write the equation. Oh, I guess I need to figure out what f of 2 is also, don't I? So that's going to be tangent of 2 over 2. It's negative 1.09. Let's call it 3. Remember that after 3 decimal places, you can truncate or round, your choice. I used to always truncate because it drove Aaron Barcio crazy. It's like, but it's bigger than, I'm like, it doesn't matter. So our tangent would be y is equal to negative 1.093 plus 3.433 times x minus 2. And our normal would be y is equal to negative 1.093 minus 1 over 3.433 times x minus 2. And again, I'm perfectly happy with that. Let's real quick try and sketch this. So I want tangent of x over x and I want y equals negative 1.093 plus 3.433 times x minus 2, and y equals negative 1.093 minus 1 divided by 3.433 times x minus 2. There's the tangent line. Oh, and there's the normal line. The nice thing about being in Zoom Trig is that it is a square, it gives you a non-elongated picture. So things that are at right angles actually look like they're at right angles. Okay, any questions about that? Okie dokie. What else do we have on here? Jerk. So jerk is the derivative of acceleration. Okay, and there is something after that. I'm sure Mr. Mosley knows what it is. I'm sure I don't. Okay? Super jerk. So let's find the equation for jerk for this one if the position function is secant of t. So the velocity will be the derivative of secant, which is secant t times tangent of t. And here it starts to get fun. Now I get to take the derivative of that, which means I have to use the product rule, yeah. So secant of t times the derivative of tangent, which is secant squared, plus tangent of t times the derivative of secant, which is secant tangent. And so now I need to take the derivative of that again. Oif. So I'm going to factor out a secant of t. And because I don't know how to deal with a squared where it's not just x squared, I'm going to write that secant squared as secant t times secant t. And the tangent squared is tangent t times tangent t. So the jerk is going to be the first factor, secant of t, times the derivative of the second factor. And in that second factor, I'm going to have to use the product rule not once, but twice.
Yay.
So that'll be secant of t times the derivative of secant, which is secant tangent, plus tangent of t. Oh, hang on a second. Back up. Boop. Plus, now I have to keep the second term. So it'll be secant t times the derivative of the first secant, which is secant t tangent t. So that's the product rule for the first one. Plus, now I get to use the product rule for the second part. I'll keep the first tangent of t times the derivative of tangent, which is secant squared t. Plus now I'll keep the second tangent times the derivative of the first one, which would be secant squared t. Plus, because I'm doing the product rule on the big thing, all of this stuff, which I'm going to put back together, is secant squared t plus tangent squared t, times the derivative of secant, which is secant t tangent t. Woof. Yeah, occasionally on these I have students who go, yeah, I turn my paper sideways. So let's see, if I distribute this secant, I'm going to have secant cubed t tangent t plus another secant cubed t tangent t plus another secant cubed t tangent t plus another secant cubed tangent t plus here if I distribute this secant t tangent t, I'm going to have another secant cubed tangent t plus a secant t tangent cubed. So there were what? Were there 5 of those?
Yes.
All right. I have no idea what's on the last page. Is there something?
It's blank.
Oh, well, that's nice.
It is notebook paper.
Gotcha. And I was like, man, did I mistime this lesson that badly? All right, y'all have a terrific weekend. And I will look forward to seeing you on Monday.
We have a quiz on Monday,
I think so.
Let's see. Yes, Monday, quiz on 3334. And then a test on Wednesday.